Hi, everyone, and welcome to this special edition of Space Weather. We've got in the house, very privileged, very honored to have her, Dr. Tamitha Skov, who is a solar scientist, knows all about space weather. And Tamitha, first of all, thank you so much for being on here. This is amazing. I know that we've connected on social media before. You've taught me a lot about space weather. I like to educate our viewers. Tell us what's going on right now. Are people going to see the Northern Lights tonight, like everybody has been commenting about?
Well, that is still sadly a question. We have a lot of answers, but we still have some questions. And the reason for that is because we do have yet another solar storm that is hitting Earth. It's hitting Earth right now. And I'm staring at behind me. You can see the solar wind magnetic field directions. But right now, the orientation of this third storm is not really conducive for creating aurora. So those folks at high latitudes are probably getting a beautiful show, but people down in the mid latitudes, well, right at the moment, it's kind of hard to tell whether or not we're going to see anything this evening.
Yeah, so that, it is a forecast. I mean, space weather is a forecast. The weather is a forecast in terms of timing the storms out. And so that big thing that you mentioned is you were talking about how that magnetic field is interacting with the Earth's magnetic field of the plasma cloud, essentially known as the coronal mass ejection. I've educated the viewers exactly what that is, but kind of explain that and how that importance of the magnetic field being southward pointing is so important for the auroras down here in the mid latitudes.
Well, it's very much like two different magnets. So it's just like, imagine taking fridge magnets right off your fridge, and you can put them together. And if the two have the same polarity, if they're both aligned the same way, they will repel each other. But if you flip one over so that one's upside down compared to the next one, they'll click, and they'll suddenly, all of their systems will lock together, and that will allow them to become a single system. And that's exactly what happens with these coronal mass ejections. As they're being shot out of the sun, they're like big fridge magnets. And Earth itself, its magnetic shield is another fridge magnet. So as long as the two fridge magnets have opposite polarities, then they'll click and we'll get gorgeous aurora like what we saw last night. But right now, the fridge magnet that's coming at us seems to have the same polarity that we do. And therefore, it's kind of acting like a bumper car, and it may just bump off us and kind of move off. And so we may not get the gorgeous aurora. So it's really as catch can, because we have no way of predicting what that magnetic field orientation is going to be prior to actually having the storm arrive.
It's funny you mentioned magnets, because great minds think alike. I've actually got magnets right here, and I'm going to be showing that on the newscast tonight with our viewers on how when you have a negative field, they repel. Positive, they repel. But when you have that negative and positive, click, it locks on. So there you go. These aren't the best magnets. I want some stronger ones, but you can definitely see it repelling away. So that's so funny that you mentioned that, because that was exactly what I was thinking. And then I kind of explained, and see what you think about this, a plasma cloud, kind of like almost like a tsunami wave that hits the Earth from the sun. Not exactly, but somewhat where that wave initially hits the Earth. Does that make sense at all?
It makes sense. And although you can't look at it from that physical point of view, it's definitely not the same physics. What is the same is kind of how it feels when you get hit by a big wave, because the initial hit seems to be the worst part of it. And that's exactly the way the Earth responds too. When these big storms hit Earth, it really compresses Earth's field. It's kind of springy. Earth's field, believe it or not, I've got my own visual aids here. Earth's magnetic field is kind of like a little slinky that you wrap around in a circle. If I had typically have a big blue ball that I stick right here in the middle, and that would be Earth, and then this would be its shield, its magnetic shield. But just like the slinky, it's very springy. And so if you crush it, it will crush down on the side that it's being hit. And so that causes everything to get really strong, and it can send a lot of energy down into the north and the southern poles, and that will spark aurora. But in order for the aurora to maintain, you have to have that constant feed of the energy from that solar storm into the system. And that's the part that's missing right now, is we had the big bang. So we had a big signal that gave us, it was like that initial jolt from the wave hitting us. But now the storm isn't able to feed us because the magnets are pointing the wrong way.
Now, you were talking about that magnetic field. I've got this graphic right here to kind of show you. There's our 7-day forecast. But as you can see, we got storms coming in. But there's the magnetic field that you were mentioning. And so what happens is that solar wind, essentially, the charged particles and the protons and electrons are emitted from the sun. And as you mentioned, and this isn't a perfect representation, but that's that solar wind that you talked about. And as that comes in, that starts to get excited, especially at the poles. And then that causes the charged oxygen and nitrogen molecules to have that essentially aurora. Now, here's a question for you, Dr. Skov. I'm going to show something here real quick. There's a lot of confusion on the different colors of the auroras and what causes the different colors. And I have seen all sorts of different heights and levels. And if you look up green auroras, NASA says it's actually nitrogen molecules. You look up others, it says it's oxygen molecules. What causes those different colors, and what are the heights essentially? I know that might not get that right off the top of your head, but maybe obviously you'll know a lot more about that.
I'll do my best. So yes, I do not know why NASA would have anything about green being from nitrogen, because that is not true. Oxygen is the heavy player here for most of the colors that we see in the aurora, for both the greens and for the deep reds. So that is oxygen, and it's actually two different what we call emission lines. And the reason for it's basically meaning that you have two different energies of particles coming down and banging, literally knocking on the door of oxygen, and oxygen having to let go of an electron. And as it does that, it lets go of light. Well, it doesn't let go of the electron, it changes its energy, but it emits some light. And as it does that, there are only certain wavelengths it's allowed to let light out of. So it ends up being specific colors. So you get the emission with green, which is actually, I believe it's a higher energy. And then you get also emission from red. Now the green occurs lower in the atmosphere than, or in the what we call the ionosphere, that which is the charged atmosphere above the atmosphere itself. But you get the green down low, and then you get the red a bit higher in the sky. So when you see green, you'll typically see it lower. You'll see red a little bit higher. And then you can actually get blue as well. Now the blue is typically, that's from nitrogen. Okay. And it's a little bit in the purple range, and it's oftentimes only really beautifully visible right before sunrise, or sometimes after dusk. It's just right after sunset. But most of the time in the very early morning. They call these like the indigo or the indigo blue tips of aurora. Really hard to spot, but that's nitrogen that does that. And then nitrogen does something else too. If you get really energetic particles that can shoot way down deep into the up into the ionosphere, what happens is that underneath, just underneath the deep greens by the oxygen, you can get these pink glowing, just the bottom tips.
Wow.
So and they look at this, they're almost glowing white. And so it ends up being kind of this oxygen nitrogen sandwich, with oxygen being in the middle and nitrogen capping both ends.
That's amazing. I want to show you, just to show you that I'm not lying about this, but check this out. There it is right there. This is from NASA, and it shows oxygen is or the green is being nitrogen. I don't know if you can see that all full screen, but I was like,
that is definitely a typo.
Yeah.
And they also didn't
too. And
they didn't put it in their correct order either. You'd think that they would start. So the pink that you see it, how they got it listed. If they put the pink, okay, that's actually tipped at the bottom beneath the green. The green should be next, and it should be oxygen. Then the next one should also be oxygen, that's red. And then the blue should be layered up at the very tip top.
Really? Blue's up at the top. Okay. All right.
Blue is up at the top. Isn't that crazy?
That's good to know. All right. Because if you look at that, you search that online, AI gets it wrong. Everybody's got it wrong. So show us some other, some other things that you can kind of talk about with tonight's aurora, if it's going to happen or not. Doesn't look likely. And explain a little more about that again.
Okay, so you've already told me that your viewers are somewhat familiar with complicated stuff when it comes to space weather. So I'm just going to go straight to something that is pretty advanced. It's a timeline that's showing actually what the solar storms have looked like over the last, in this case, 24 hours. And over here, So I'm just going to concentrate on this big panel over here. You can see all these squiggly lines, and there's a bunch of them, but this is really the magnetic field that we're looking at. Okay, so as our upstream monitors go through, have the solar storm pass through it, they actually measure what the magnetic field is just right all around it. So that's what we're seeing right here. And this is really strong. You're seeing numbers like 40. I don't know if you can read the numbers, but you're seeing things like 40. Here's 0, here's 40, here's probably 80, minus 40 and minus 80. That's pretty strong for a storm. Our storms are typically about maybe 10 plus or minus 10, plus or minus 20 gets to be a pretty big storm. But plus or minus 40 is quite big. This is why we're already dealing with G4, almost G5 levels. The biggest, I think the deepest part, and if you look at this red line, so red is danger, Will Robinson. So it's a good color for this particular, because this one talks about this northward and southward component that we really care about to make those magnets click. And so the southward component, which is a negative going below 0, was really, really strong the other day, right? This is why we got so much good aurora. It went up to 0, kind of hovered a little bit, and then went down again, and we got another really good patch of aurora. And this is when the United States got to see it, because it was nighttime. This is when New Zealand and everyone down under got to see it, because it was also nighttime then for them. And then we popped out. Notice you see this pretty like structure, really strong, really kind of a beautiful oblong, almost egg-shaped structure. That is part of the core of that storm, close to the core, not quite. Then we popped out into a different set of structures. Notice though that the red line went above 0. So basically from that point, from last night, we've still been in some strong magnetic field from these storms, but it's all been northward, meaning the magnets aren't clicking anymore. And now we finally got hit by this last one, and I'll blow this up here in a second. But as you can see, why I wanted to keep it like this is because you can see it's not quite as strong, right? It's still strong, almost 40 nanotesla, at least the start, but this one was much bigger. This is the weakest of the 3. Okay, and sadly, right now, the magnetic field is still staying reasonably northward. However, and I'll blow this up in a sec here. Let me see if I can, if you have the time to look at this spaghetti.
You can get it flip pretty quick, can't you, sometimes, where it's positive,
yes,
positive,
we can.
all of a sudden it just flips.
We did even have a short period of it. And in fact, that was a big warning sign. I had a lot of people contact me and say, hey, the magnetic field flipped southward. Is game on? And I'm like, no, is it flipped back north?
Yeah.
Not yet. But you notice it is beginning to come down. So we may yet see this thing cross into negative territory, and we still have some strong magnetic field here. As a matter of fact, we're sitting at what? The total field is 22 nanotesla, which is a lot. Like I said, the average storm is between probably 10 to 15 nanotesla. That'll give us like a G1-ish. If it's really southward field, then we could get maybe a G2 from that if it's long or sustained or fast. This is actually stronger than that at 22 nanotesla. That's the white number, okay? And we are moving really quickly. What's this say now? What does that say? 808 kilometers a second? We are accelerating, and that gives us a hint about something. Solar storms typically don't accelerate unless something's pushing them from behind. So we may have yet another hit, and that, if you don't mind, if you will indulge me for one more moment.
Oh yeah, absolutely. Take it away. This is expertise. I've just been trying to explain everything as best as I can, but you are the expert. You're the doctor. You're the solar scientist, solar physicist.
Well, we still get them quite wrong. We're about, just so everyone knows, space weather forecasting is about where terrestrial weather forecasting was back in the 1950s. For those who remember, and I'm serious, we have barely more than a tornado siren right now, because we cannot predict the magnetic field direction. And we have, and the analogy I use, because we can observe the solar storms coming off of the sun, but pretty soon they become they're like jellyfish. They become very transparent, and pretty soon they disappear from our view. And so we have to wait almost 99 million miles for these things to arrive at our upstream monitors before we're able to see them again. So trying to forecast that and what direction it's going to be and when it's going to hit is kind of like trying to forecast when a car, imagine this, imagine a car is going to drive from New York to Los Angeles. And the only thing you have to guess when it's going to arrive, to time its arrival, is basically the speed at which it backed out of its driveway in New York. That's it. That's all you got.
That's it. That's all you got. Now we are increasing that technology a little bit, aren't we? We're having new satellites that are going out. One that's going to be replacing. Then you, of course, Discover is, like you said, 1 million miles away from the Earth. What is the newest technology that's going out there? Will it measure the polarity of the magnetic field?
No, sadly. I mean, it's still in the Earth's system, right? We're still sitting just upstream of Earth. What we need are satellites, or really spacecraft, that are way ahead of Earth, kind of like the way Solar Orbiter is right now. And it's way ahead of Earth. And so it's able to give us a little bit of a forecast, but that spacecraft doesn't park there. So we still have quite a ways to go before we're able to kind of afford the technology. We have the technology, but putting it out there in space and having it be way upstream to give us a really good heads up of what's coming toward Earth is actually still a bit out of reach right now, at least financially for us. So we'll just have to keep puttering on with this as long as we can, because at least until our technology gets to the point where the pain threshold, we cross that pain threshold for everybody.
Well, but let me do this real quick, Tamitha.
Because I want to show you this.
Just to show our viewers. Yeah, go ahead. I'm going to bring that up full. Okay, go ahead.
Are you sure? Okay.
Yeah.
I don't want to hijack your show here.
No, it's all about you and space weather. So I love to hear this. Yeah.
Well, here's the thing. Remember, we talked about just a moment ago that it looked like that solar storm was actually accelerating a little bit, like the speed was kind of going up. And I can show that again to remind everybody. This speed right here, this is the yellow. If I slide this down, this is the yellow trace here, and it's like, kind of ratty. But look how you notice it's trending upward.
Yeah.
So it's going from about 800 kilometers. It's kind of just going. It slowed down a little, but it's accelerating up. I would not expect that to go a little bit faster. That's not what I would expect. So there's either two things. There's one of two things happening. Either we have another transient, another solar storm that's hitting us, and our third one hasn't quite reached us yet, or there's some really fast wind behind it. And I don't think the fast wind has been slated to come yet. Look, it even crawled up a little bit higher. This is about to go off scale. So they're about to have to raise the level here. We'll see what happens.
That's quite a bit. I mean, nearly 1,000 kilometers per second is a pretty fast solar wind.
Yeah, there's definitely, you have to use your screen here. That side. There's definitely something, there's a little bit of noise in the data, because 1,000 kilometers a second is pretty fast, but it definitely is telling me that I think there's something coming. Plus, let me show you this. This is the one I wanted to show you. This data here, once again, line diagrams. They're so boring, I know, but sadly, this is all we have when we look at stuff that's just ahead of Earth. We don't have images to show.
Yeah.
But the line diagrams, you see this slope, and it's continuing to go up. Usually, when you get hit by these solar storms, these were what we call super thermal particles. Doesn't really matter what it means. It just means that if there's a shock coming nearby, it energizes particles. It energizes these particles. So the numbers will go up. In other words, the lines will increase, okay, because there's more of them. So as this increases, once the shock passes over us, it will peak and begin to go down. Okay, so that means that the solar storm, because there's always a shock wave in front of the solar storm, as it passes us, it goes away. And because the shock goes away, well, then the particles begin to drizzle out, because there's the thing that was creating them is, moving away from us. So you would expect this what we call fluxes to, instead of increase, they would begin to decrease gracefully. Well, that's not what's happening. They began to decrease. And so I was like, okay. But then we got a bump up, and sometimes that's no big deal. It's just a little bump, and then it goes back down. But I'm noticing it's not going back down. And if I zoom in, see, this is 3 days. If I zoom in a little bit more to, let's say, the last 24 hours, I don't know. Really see that. There's something going on. Is it dying out? I don't know. Maybe, maybe not. So this is why I say we've answered a lot of questions, but we've also asked a lot.
Yeah.
So I think we're just going to need to pay attention. I would say if you're a diehard or aurora chaser, it might be worth a look. because it looks like the field might be flipping into negative territory.
Starting
For
to flip
those,
negative.
for
Let me ask
those
you
who
this.
are, yeah, sorry.
Is there a delayed process? So when it flips negative, I noticed that it flipped negative, and what we saw was it took about an hour and a half, about 90 minutes. Once that flipped really negative, got down, like we said, the BZ got to negative 50 from yesterday evening. It took about an hour and a half for us to see the aurora here. Obviously, it was daytime too with the sun up, but is there a delay as to when it shows on Discover and by the time it hits us, essentially?
Yes. Now there's two ways that delay occurs. The first way, of course, is that Discover is ahead of Earth. It's about 450 Earth radii ahead of Earth. So it's going to take a little while for that solar wind to actually hit Earth itself from our upstream monitor. But that is dependent upon the speed of the solar wind. So when you have super fast solar wind like this, sitting at 800 plus kilometers a second, you have maybe about 15 to 20 minutes, maybe half an hour at most, of a leeway, of head lead time. When the solar wind speed is much slower, like a typical solar storm, which sits, I don't know, anywhere between 400 and 500 kilometers a second for an average storm, you have up to about an hour. Okay. So it really depends upon how fast that solar wind speed is as to how much lead time you have, because, it's like a race, right? The faster runner gets there sooner.
Yeah.
So that dictates that. Plus, you also have to consider how the Earth responds. And if you actually go to the GOES magnetometer, I don't know if probably most people do not know about this.
All right. Yeah, some people do. I've seen it, but the total. Yeah, go to that.
If you go to the GOES magnetometer and you pull it up, okay, what you end up seeing, and I've got a lot of days here. I'll just leave it like this. What you look at. Oh, and I can't see it on that side, so I'll do my best. My TV's dead here on this side, so I can't see what I'm doing.
Yeah, I know we've done that before, doing weather and all.
It's like what happened? Okay, yeah, the monitor's out. So if I look kind of strange, I apologize. So this is when the first set of storms hit, and in actuality, one of our spacecraft actually jumped out into the magnetopause for a sec. For those who know, it actually because the Earth system got really crushed. But what you end up seeing is a lot of this up and down, up and down, up and down. And you also see this nice smooth kind of, undulation, right? You see it here. If I go to 7 days, you'll definitely see that nice smooth undulation. This is what the Earth's field looks like when the satellites go through it, when there's no disturbance. Obviously, disturbed field looks a bit like this, but you can tell something from these wiggles. Okay. Now, granted, there's lots of wiggles this time. But if I zoom in, I'll zoom into the last day.
Kind of reminds me of a seismograph a little bit, like an earthquake,
Kind of does, doesn't it? Let's see if I can make it a little bit prettier.
Obviously, totally different, but just in terms of the lines when the squiggles happen.
When the squiggles happen. What you end up looking for are squiggles in which, let me stand on this side again. What you end up looking for are squiggles near the M, not the N. N means noon. M means midnight. So if you are watching the data anywhere around midnight, which means, sometime in the dark when it's nighttime.
Yeah.
You're not going to be looking for aurora during the day. But these spacecraft are aligned with Earth. So when Earth is dark, then the GOES spacecraft are also, they're kind of like in the same time zone. This is the East time zone. This is the West time zone. So Eastern time and West, Pacific time. When Pacific goes through midnight, so will the blue trace. When Eastern Standard Time goes through midnight, so will the red trace. So they're aligned with the United States because the GOES satellites are really trying to tell us what the space environment is for our continent. Okay, so that's one nice thing about living in the United States. We get a little bit more data than other people do. So what you look for is when the magnetic field jumps up. When it kind of goes down, it's charging the Earth's magnetic tail, kind of creating like a slingshot. It pulls it back, and that's cocking it back. And then when it pops up, it's releasing. So it's like you're pulling a slingshot back, and you let go, and it slams forward. That's when it's shooting particles into the northern and southern hemispheres and creating aurora. Okay. So those who want to read. Yes. So when if you want to see when, and then we call these substorms. And so when you want to know when these substorms are going to occur, and what they cause is a brightening of aurora, sometimes for about 20 minutes. You follow this and see when these lines jump up, especially anywhere in and around midnight, and you will watch and you will see within 10 minutes, you'll see the aurora begin to really brighten. You'll see all sorts of cool things, little auroral beads, and then it'll brighten and then it'll move. And yeah, so you can really use the magnetometer data if you are someone who chases substorms. So.
That's cool. That's cool. That's something that I obviously did not know, but I've learned. That's really awesome. But real quick question, and then I want to share some of our viewer photos that we had. So obviously there's a lot of talk about, this is going to be really, really bad for the earth. And, people are going to spontaneously combust, like the movie Knowing, and,
oh my goodness,
Hollywood. Yeah. I know, exactly. So what does this mean for us in terms of what are the dangers? Are there dangers of this solar storm? And, I've seen a lot of comments. I want to hear it from an expert. What does this mean for us, and how will it impact us?
Well, if you don't mind, I'll show you some of the biggest issues that we have. And I don't think you guys can see good. Hold on one sec.
While we're waiting, while you're bringing that up, why don't we look at some viewer photos? You want to do that?
That'd be
real
great.
Quick?
Yeah.
Okay,
yeah.
Let's check this out. So we're going to bring up, first of all, we got several of these. Check these out. These are from Northwest Arkansas. And I mean, people were loving it because we were telling them the Northern Lights were out there. We did a live update, and we'll just kind of, cycle through all of these. But we're getting the greens, the reds, even a little bit of pinks. Of course, cameras will take different colors at times, different quality cameras. There's Sam's picture from Havana, Arkansas. You've got, I thought that was Cuba there for a second. And then our meteorologist, Aleshli Castro, I was like, get out to that high spot. And so we sent them out there and they got to see the aurora. Here's one from Newton County, which is just a little east of Fayetteville, 2 counties east of Fayetteville. Check out that one from Dave. Just beautiful over Prairie Creek. Again, this is all from last night into this morning. Even Fayetteville, and you could see it with the naked eye, and it was very visible, but it only was really visible during those substorms. So when those substorms are going to occur. Here's Laura Gentry with a photo from Bella Vista. And yeah, those colors were amazing. And the time lapse is really cool, as well as we showed how the aurora kind of dances. Pea Ridge. And we've got one more here from Cheryl. Look at all those pictures. So that's just a handful of the ones we got. And we got a ton. So, all right, take it away, Tamitha, with what does this mean for us?
Okay. So one of the things that you can see behind me is a big red thing, and I'll talk about that here in just a second. My green screen is kind of going wonky on me, so let me turn a little bit more light on here. Hopefully that helps.
Yeah,
so good. So some of the things that we've been concerned about, of course, when we get these really big storms, is certain aspects of our infrastructure. Now, most of the time anymore, especially with the Gannon storm that we had back in May of 2024, we've gotten a lot better with our power grids. But believe it or not, there are some power grids that have been stressed, not so much in the United States that I've heard of as of yet, but there were some warnings put out for the New Zealand area. I know a few people that work for TransPower, for example, and I'm waiting to hear back from them. Hopefully they got through everything okay last night, but they're very proactive. And so they protect their grids really, really well down there. So, and they're very space weather savvy. So I'm very happy to hear that at least thus far, no horrible incidents. But that's something that we always worry about, because believe it or not, the aurora and everything that happens as these particles get shoved down into our upper atmosphere, they can create currents, electric currents up in our atmosphere and down in the ground. And those currents don't like to move through rock because it's kind of like a jam-packed highway, right? So what they want to do is they want to short circuit that and get out of there. And so they couple into our power systems and give us essentially green energy. It's free energy, but our power grids don't know how to handle it. And so they get overloaded. So that's one of the things that we have to worry about when we have these really big storms. Thus far, it looks okay. One of the other things that's a kind of a bigger problem for us, at least right now, is in our GPS systems, our GPS and our GNSS. These signals, the signals from GPS can oftentimes just get a bit degraded during during big storms. Aurora has a tendency to make GPS signals do what is normally very beautiful. If you ever park out on the city lights and you see the twinkle of the lights in the night, and how beautiful that is, or you see the twinkle of the lights in the stars in the sky, it's a beautiful thing when it's a visual, representation. But Aurora will make radio signals do the same thing. And that's not so great when you're trying to figure out where you are. So the GPS will basically tell you you're someplace you're not. And that actually happens. That's actually what's happening behind me here. This is the FAA we call it WAAS, the Wide Angle Augmentation Network System. This is what helps airlines land their planes using high precision GPS. And as you can see, when this 24 hours, the last 24 hours starts over, because we've been pretty calm right now. Everything in blue is good, but everything that goes red is bad. And you will see, not only does it come in, but it almost completely eclipses everything in the United States. So I guarantee you there were no TAMs issued last night because of the degraded GPS performance. Airline pilots know how to deal with this, but it is an issue and they can't ignore it. And so substorms are a reason why this happens. Also, we've got some precision agriculture issues with GPS as well, just like we had with the Gannon storm. Everything in precision agriculture now is run by GPS. So these types of issues are kind of spreading because GPS has become so ubiquitous. So that's a big issue that we're dealing with now as well.
I got you. Okay. Well, that's some great information. So let's go back real quick. Let's look at the very latest and just kind of recap. Are we going to see another solar storm like we did last night and the Northern Lights display? That's the big question. I know that's what everybody wants to know. We'll close it out with that. Give us your insights.
Well, it's not, even if we do see another solar storm, even if we do get that back, I do not think it's going to be as strong as what we saw the other night. Let me get back to real-time solar wind so I can check just this one last time if it will load for me.
See, I heard a lot of people mentioning, "Oh, tonight's going to be even better," and I was like, "Don't count on that," because it's always that the first opportunity that you get, that's the one to seize it and take advantage of. That's why I sent Alesh and Davion out there. I was like, yeah, I know that. And another thing too is Z time is confusing to people because they were talking about G4 geomagnetic storm happening between 3 and 6Z, but that's actually last night into this morning. So
so if you're dealing with Zulu time, right, you have to be careful because it's not it's not the same as the time in the States.
Nope.
So
you have to convert too. So
so you have to do the conversion. That's the first thing. Let me see what I see here. In
we'll
this
wrap
case,
this up here soon, but what are we seeing here as of the latest? And this, by the way, we recorded this. It's ending at about 4:45 Central Standard Time.
Okay. So this is right here where we are. Sadly, as we were watching that magnetic field go southward, which is what this trace is here, it's now bumped back up again. So I just don't know. I think there's a chance because the solar wind speed is so fast, even a small southward field could get us some aurora. So if you're a diehard chaser, it might be worth a look, but you're going to need to be patient and you're going to likely need to chase those substorms.
Well, thank you so much, Dr. Tamitha Skov. I appreciate it very much. Like I said, I'm always impressed by what you do on social media, the YouTubes, the live streams. Tell us how we can follow you and all of your socials, if you will.
Oh, thank you. Yes, you can find me on Twitter at Tamitha Skov. You can find me on Facebook at Tamitha Skov. During real-time storms, I'm typically on Twitter. And of course, you can catch my forecasts. I do them essentially once a week on YouTube. And that's, again, just search for Tamitha Skov on YouTube and you'll find me, or the Space Weather Woman.
Appreciate it so much. Thank you so much for educating our viewers on space weather. And you have a great night.
You too. Thanks so much.